over there.
So today I welcome all of you. This is this talk today. It's mainly based on astrophysics, and first talk will be on solar physics, and the second one will be on 30-meter optical telescope. So for first talk, Dr. Sreejith will present. So I'll like to invite Anand to give introduction for Sreejith.
Thank you. It's my pleasure to introduce Dr. Sreejith sir. So he did his MSc from IIT Madras. After he obtained his PhD from ISRO Satellite Center, which is currently known as URO Satellite Center. After that, he did his postdoc in Trinity College, Dublin, Ireland. And he was here at MCNS postdoc for a brief period as a postdoc. Then he joined IUCAA as a project scientist under Aditya-L1 project. And he's currently playing a key role in development of one of the instrument on board Aditya-L1, that is solar ultraviolet imaging telescope suite. Recently, he has joined back to MCNS as assistant professor, and his interest actually mainly lies in solar physics and space instrumentation. So today he will be delivering a talk on Aditya-L1, India's first dedicated space observatory to study the sun. With this, I will invite Dr. Sreejith sir to deliver what this.
Thank you, Arun, for introduction. Today is first time we are going to astrophysics, astronomy talks. In this series of talks, we are having over a week, and since I am having the first astrophysics talk, I would start with slightly on that. And I would just for everybody's knowledge, there is a talk after me on astronomy again and again on Monday, 2 talks. So I will be talking here about Aditya-L1. Here, which is happening from my computer, I think. This problem came last time also, right? How do we this go around, sir? Okay, it's gone. It's gone. It's gone. Okay, sorry for that glitch. Okay, I'll be talking about Aditya-L1, which is India's first dedicated space science observatory to study the sun. I'm here at Manipal Center for Natural Sciences, and my email ID is given there. In case if there is any questions which are not able to ask here or unanswered here, please feel free to write to me. I will get back to you. Take that. Sorry. Yeah, sorry for that. I'm sure I'll use the slide sheet. Okay. No, it's not okay. Let me just check. What's that? Okay. Okay, I'll use this mouse and change it. When we talk about astronomy, I would confidently say that astronomy is the cradle of physics. I can give 1 hour talk on just on that alone. because it's a big topic. If you think of any legends of physics, let it be Galileo Galilei or Sir Isaac Newton or even Einstein, you take any legends of physics, at some point of their career, they would have spent their time, especially early time of their career, they would have spent time on astrophysics and astronomy. And the reason is very simple. From very time immemorial of the beginning of the civilization, if you look at, people are curious about this thing, right? You, from your childhood, even if you think when you started liking science, one thing you would have surely, of course, there will be many things in your life around your house, like you were hearing yesterday. But one thing you would have generated the curiosity in you would be the stars or the moon or the sun, which, you know, as a very small toddler, your mother would have shown the moon to you and maybe feeded you or would have told that, look at that moon, it is your uncle or whatever. This is something which would have first struck you as a very small child, captured your imagination, curiosity, that artistic instinct in you would have come from something from the sky. So astronomy is something which would have generated that scientific temper inside you at very, very early childhood. And another point I want to mention here is, like yesterday we were discussing, or many of these days we were discussing about science which is directly influencing your life. I'm talking here about a science which has no influence in your life, to be very truthful. Whatever I'm showing here don't have any direct influence in your life. The stars or the moon may not, okay, moon might affect the tide and all, but talking about the water or the soil or the forest or the things like that, these faraway black holes or active galactic nuclei, which you have heard many talks here, has no influence in your life. In your lifetime, it may not matter what happens there at all. But still, people study that. Why? So that's why I want to bring you to another part of science, which is cannot have any influence in your day-to-day life, but something which, you know, trigger the curiosity in you. So there is also an academic part of the science. What I'm trying to say is that unlike what we discussed all these days, which are very important, which affects your life, there is also a part of science which many of the great people, philosophers have spent time on, which don't have any direct influence in you, but it generates a curiosity in you, it creates an academic interest in you. You want to know. It's like you say a light far away on a hill, which don't have nothing to you. It's very far away, there's a light or something on the sky. But still, you won't get sleep until you know what that light is, what's happening there. You may start thinking, you may try to go there, see, call your friends, see there's some light there. So there is a branch of, or majority of, or I will not say majority, that may be controversial. There is at least one section of science which is driven purely from this human curiosity. And all these people who study this academic science very well know that it may not have anything to do with your life, or I may not be able to do anything. But still we study that, because of that gives us some happiness or some fulfillment feeling. It's like an artist drawing an art. You may not get anything by doing that on a wall, but still he does that. Or somebody who sings that in your bathroom. You know that it's not a performance, nobody pay you, but still you sing. It gives you some happiness. So I'm talking about a branch of science. Astronomy is such a science which lot of people, it interests a lot of people do research in this, but still I cannot, if somebody asks me this question, okay, fine, all this, but why should I fund you? What do you get from this? I don't get anything directly, but indirectly I get many things. I'll come to that. There is a lot of spin-offs, there is new things which have come up indirectly because of astronomy. As I told you, the physics, that's why I put this, it's a cradle of physics. You don't gain anything from that, but when you grow up, it can do a lot of things as a secondary or a spin-off. From time immemorial, you know that human beings were curious about the sky. When you saw some things blinking in the sky or twinkling in the sky, you try to look at it more closely. People started using telescopes. Of course, telescopes were not invented for astronomy purpose. It was for other purpose, like in shipping and seamen and all. But when telescope became popular, people started looking to the sky as well to see whether we can improve our knowledge about those things, the celestial objects which are there on the sky. And later, I'm just jumping into to the modern age. Whatever you see with eyes is on this side, and what you see, if you take a photograph of that in particular wavelength, which again I will come to, is here. It's the same feed, it's the same place, or same part of the sky. You can see the same part of the sky when you look to the eye. When you capture it using a camera, using certain exposure times, certain filters, etc., is really different. This is what triggers the curiosity. Why this photo looks different from what I saw with eyes? There is something there, right? These are the things which triggers this curiosity or the basic academic interest in this. Okay, so where we are as of now, I'm not going to astronomy talk, my topic is totally different, but I'm just giving an introduction. In the part of universe, if you zoom in, we are very, very tiny part. This is one of the galaxies. You know there are 10 power 11 galaxies. When you say 10 power 11, I put 1 and 11 zeros. There are so many galaxies. In that, one of the galaxies is our galaxy. In that, again, there are 10 power 11 stars. And that one of the stars is the small sun. It's a small normal star. And we are such a tiny part. And we are sitting here and we are looking at this place, like where we came from or how big part of the big universe we are. Okay, this is just again, but my interest of topic here is not the Earth. My interest of topic is studying this part, which is the sun. Of course, sitting in Earth or going around Earth. And I will be studying sun, or I'll be discussing today about the sun, which is one of the bodies of this 10 power 22 stars, and maybe another 10 power 22 celestial objects, which including planets and comets and all those things. So I'm talking about something like you put 1 and something like 50 or 100 zeros after that. How many objects are there? I'm just talking about one object in that. And I'm afraid I'll finish in 1 hour's time. And so I can talk about 1 and 10 power 100 similar objects. People can talk about it. The sun is important because it has been, again, part of our civilization history. If you take the very oldest architecture or paintings, you will see the sun. And the sun has been always like a king or a sun god. Everybody, because it's something which you are seeing every day and it has a direct influence in your life. The sun is a very normal star. In these photos which I showed you, it's a, I would say, boring star that way. It's a normal star, middle-aged. You know, middle-aged is people who are interested. If you're youth, you're a lot of it. Youth are think that if you're old also, you become very interesting personality. Middle age is the boring part of your, nobody's interested in the middle-aged people, right? So sun is a middle-aged star. There's nothing. If people, astronomers, you talk here, the students and all, they will say, what's either should be star forming region or it should be a red giant or something happening, black hole, where it's a end of the death part of the sun, star. Sun is nowhere near that. It is just a middle age. It is 4.5 giga-year-old and there is another 4.5 giga-year-old life remaining. And it is again a main sequence star. I'm not going to the technicality, but people know astronomy know that main sequence is again a boring place. There's nothing happening there. It's just all stars and a lot of stars are in that region. So that way sun is a middle-aged star. But still, I'm talking here and many people study star because sun is also a special star. It is not, though it is a middle-aged boring star, it is also a special star. Because it's the only star which we can resolve. By resolve, I mean all of the stars which I showed you, whichever telescope you use, the biggest telescope you use, you will still see those stars as a dot. Every star is a dot. You don't see what is happening in the star. You cannot resolve the surface of the star. But sun is the only star we can resolve. The reason is very simple, it is nearby. Okay, when you are looking at very far away, when you see an aeroplane going on the sky, it's a dot. When it is nearby, you can see it, resolve it, right? Similarly, since it's nearby, you can resolve it. And it is the only star. So if you want to study what is happening on the surface of the star, inside the star, only option we have is sun. Hence, that makes a very special star for us. And of course, it's our star. It is, our star means that's a star which anchors Earth around it. It's a star which produces all the energy for us. It's a star which gives us almost all the energy which we require. Once I gave this talk and somebody asked me what about radioactive energy, uranium or this one, is it? And if you look at that answer is still, We have all those elements above iron because it came from a star. Again, astronomy people will understand what I'm trying to say. If you have any element which is bigger than iron, it would have come from a star only. It cannot be formed on Earth. All this fusion, or any element to be other than hydrogen, it has to get fused, no? Fusion would have happened in a star. And obviously, if you find any of them in Earth, it would have come from sun. So sun is providing almost all the energy we require for our livelihood. Also, sun is a very special star because it provides us a very unique laboratory, which we can learn a lot of physics. For example, let it be fusion or let it be particle. It's a laboratory which you cannot create on Earth because our technology is not grown up to that. But it's happening on the sun like a window. You can peep into the sun and just study that. And you know what's happening on the sun, how the energy produced on the sun. 2 neutrons and 2 protons join together, and when a helium atom is produced, or a deuterium is produced, it produces a lot of energy. That's what coming out as energy. Again, I'm not going to repeat this of that. What happens on the sun when this fusion happens at the center, as you can see here, if you can see my mouse screen cursor, here is where the energy is happening, and the energy is pushed out. And when it is pushed out, it produces a lot of, it's like an explosion happening inside the star or inside the sun. Like huge explosions, nuclear, it's like a fusion bomb. You think of an atom or a hydrogen bomb, think of like hundreds and thousands of lakhs of hydrogen bomb. Maybe it's the right time to talk about bombs when wars are happening around the world. Imagine there is a lot of hydrogen bombs happening at a time, how big the explosion will be. It's an uncontrolled fusion happening here. There is nobody to control the fusion. It's like uncontrolled bombs burning there. When it happens and when this push happens, what we expect is the star to burst out, right? Because it's like a cracker. When you fire it, it bursts out. When such a fusion happens inside, it should burst out, right? But still it doesn't burst out. Why? Why? There is gravity which is pulling it back. So there is a reverse force which is happening. Okay, this is exactly, I was just showing the previous one, that rotational thing again. Let's not go to that. So what I was showing previously was that at the end there was this rotational thing happening. It is called convection. I was just showing those movie of actually this convection happens on the sun. What I showed earlier was a video of that convection cells, just to show that this thing what you see here really happens. So you have this explosion happening inside, and at the same time there's a gravity which is pulling it back. So it is two types of force here. One thing which is pushing it outward because of the nuclear fusion. Then there is gravity which is pushing inward. So this up and down, this happens. And if this happens, what obvious thing which can happen is you can think about these vibrations of waves produced. Because there is something which is pushing, something is pulling back. This motion will produce a lot of waves on this sun. And just like Earth has this seismological study, in sun there is a helioseismological field. A lot of people study helioseismology, and that's the only way to study the things happening inside the sun. So there are two pressures here. There's a pressure outward, gas pressure, and then there's the gravity which is balancing the sun. This is true for all stars. But as I told you, the only star which you can study this or observe this in high resolution is sun. And we see this in the sun, and we know that that is what is happening in all the stars. So you can see here. Sorry, I just made this movies. So you can see here, this is an actual data, this is an actual image, actual movie. You can see a lot of waves happening here. All sorts of waves. And there are different modes of waves. You would have heard about modes of waves, like G modes, P modes. Let's not go to that. Like, you can see here, like some waves can go very deep inside and form. Some waves may be surface waves. So there are different types of waves. And when you vibrate something, you know that produces sound, right? You take anything and vibrate it, it produces some sound. So when sun vibrates, it also should produce sound, right? So you have heard about all these WhatsApp University stories about the sound of sun. Again, it's not actually the sound of sun. but it is not the sound of sun which comes in WhatsApp because you cannot hear that clearly. It's okay. I don't know how I can. I have recorded that. Actually, there are two types of sound. One is 3 minutes oscillation. There is 5 minute oscillation. You take anything and creates a 3 minute or 5 minute. You can hear that sound. If you have played that sound, I have that audio wave, but you won't hear anything. It's just some. It's like some radio station where you don't have any signal because it's just plain sound. There is no. It's not any. There is no particular sound like you get in WhatsApp or in Facebook or social media. But suns make sound. Sun does make sound. And sun has a lot of structures, interior and exterior. There is fusion happening, and then there is the photons or whatever the energy travels all the way to the surface, and from surface it comes to us. It makes something like random walk. And the interesting part, a photon which is produced inside from a nuclear fusion, it takes almost like 10 power 11 or how would I say, millions of years to reach outside. The photon, we see the sun after 8 minutes, we know, right? So, but that photon which I see got produced inside the sun during nuclear fusion millions of years before. Because the density is so high, it's like if I fill this auditorium with 1,000 people, and if I tell Krishna Mohan to come to the stage, he may take 1 hour to reach here because there's 1,000 people here. He has to push through every one of them and reach here. You would have seen it in some award functions and all. You call somebody, it takes a lot of time to reach forward. It's the same thing happening on the sun. It's so highly dense that this photon has to push through all these things. It has to scatter to reach the surface. And as it does, what happens is, just like if I tell him to come here, he might reach here after 1 hour pushing through this 1,000 people. By the time he reaches here, it will be totally devastated. All his energy would have been lost, right? Because he has been doing this activity. Very same way, the sun which produces at the thing, which is in a very high gamma ray, by the time it reaches the surface of the sun, it loses all its energy and it comes to ultraviolet range. And when it comes to ultraviolet range, that is the range where this plasma can absorb that. Till then, the energy is very high, it cannot absorb, it was scattering. At some point, this plasma will absorb it, and when it absorbs it, it becomes like a black body. You would have heard about black body, right? In your +2 and all. All of you would have heard about that in schools. Something is like a black thing which absorbs the things inside and re-emits. So this plasma absorbs this energy and re-emits. It's all fine, but there's a big problem here. When there's a black body which absorbs the energy from inside and emit outward, you lose all the information from about inside. You cannot see inside. Only what you see is the surface, because surface is re-emitting. So because of that, let it be sun or any star, you don't get any, you cannot see inside that. Only surface you can see. So the sun surface you can see, you cannot see inside the sun. Whatever telescope you use, whatever wavelength you use. But how do we study things about inside? How do an artist make this drawing? Only using seismology, just like Earth. Unless you dig inside, you have it. Okay, if you go to the sun and dig inside, you will be able to see inside. Unless you do that, like Earth, if somebody is there from outside, like a satellite looking, what you see is the outside surface. If you want to know inside, you have to use seismology, the vibrations of the Earth, study about that. Same way, sun also, if you want to study inside, the only way is used to helioseismology, which I was just talked about. Otherwise, there is no information. Whereas, the place where the emitting happens, from there onwards, even if there is some cloud outside and all, you can study that. Like if there is a source here, you think of a light here, and there is something here, I can study about this. Because my source is here, something is here, I can study spectra, so many ways. There are different ways of studying the change in polarization of the light, studying the spectra. You can study about the object in the front. There is a light and there is something in the front, I can always study about that. So whatever I'm showing here, outside the photosphere, which is called the atmosphere of the sun, that we can study, actually take photographs using different methods, which I'll come to in a moment. So all the photographs of the sun, what you see in different wavelengths, are from the surface of sun outward. That is what we see always. And solar physics is of course connected to a lot of different branches of physics. As I told you, you study about this physics, you study any great astronomer, Let it be Galileo Galilei, Kepler, Newton, Einstein. They have worked in astrophysics, they have worked in solar physics at some point of time, connected to sun. As somebody told the other day, Newton would not have, it would have been impossible for Isaac Newton to derive 1 by r square relation without studying astronomy. Because you do any experiment on the sun, on the earth, you cannot find that 1 by r square. You need large r to get that 1 by r square relationship. Because he observed these planets going around, he could derive that relationship of 1 by r square. And you know, as I told you in the beginning, it was pure academic curiosity, nothing else for Isaac Newton to derive that. He never thought that we will launch a rocket at some point where I need this equation to solve my rocket dynamics. It was his curiosity. And the curiosity led to these equations of gravitation. And you know now, if you want to do any space physics, if you want to send a javelin throw, you should know the different equations of motions, right? Or if you want to send a rocket, you want to know the gravitational equations, right? Equation of gravity. So, though it was science developed from curiosity of human being, it has a lot of output, secondary outputs. It leads to a lot of technology and other things. Just one example. Galileo Galilei was the first person who started studying the sun in a very systematic way. I cannot say he's the person who started studying the sun because sun is studied from time immemorial. You take any ancient scriptures of Indians, Ramayana, or even Chinese, 2000 years old records are there of studying the sun, studying these dark spots which Galileo observed. Galileo told these are the pimples of the sun god, for which then clergy was very unhappy against Galileo for saying that sun god can have pimples. Because when he looked through telescope, he saw these black marks on the sun, and he reported it. These are his actual drawing. You can see he has drawn on the paper looking through the telescope. These are the real drawings, photographs. He saw that, and he told that there are problems on the sun. It is not as good or nice face. There are pimples. And if you see, there are mentions about that in Ramayana. In fact, in my thesis, first page, I put that. There are mentions of that in Chinese ancient texts of 2000 years old. Many ancient people knew there are black things on the sky because it's a visible object. You go to a beach without any pollution. Still, today, there are two sunspots on the sun. You can see it with naked eye if you early morning, if it is a very nice unpolluted area. Because these sunspots are naked eye objects. So, but problem is, there are studies from very time immemorial, but there was no systematic study. It was just curiosity, they recorded it. Whereas Galileo started systematically studying. Every day he will observe. Is it moving? What is happening to that? He started systematically studying. And he asked this question, what is it happening? Initially, people thought that these are burned out regions. They thought that just like in your in a chula or your kitchen, when burning is over, it becomes black color, right? If you wood, you burn. So they thought that these are the regions where burn, dark region, ash. It's become ash. Later, people understood that no, it's not ash region because the same region sometimes disappears. If it is an ash region, it should remain the same always, right? And Galileo understood it is not a region because it is keep refreshing. And interestingly, though Galileo observed it in 1600s, life of Galileo was in 1600s. Galileo observed it in 1600s, but till very last century, till 1900, 1908, nobody could understood why exactly this is done. The exact explanation came after 300 years. People studied it for 300 years. And the size is very big. As I told you, if I put Earth here, just for scale purpose, it's not that the Earth sits there. Just for scaling purpose, I superimpose this. You will see that it is much, much bigger than those small dots are much bigger than Earth. Okay. But again, I'm coming to my topic. I'm sorry, I'm still entering my topic. I told that Sun is going to be studied using a satellite called Aditya. And you may ask this question, Sun from space, why? Sun is so bright, you can see from here, so hot. Why you want to go to space to study the Sun? The problem is, all the things from the Sun won't reach us. This is, the x-axis is the atmospheric opacity. Opacity means how much the atmosphere will block the light. And y-axis is a different wavelengths. You can see that radio waves, everything comes to Earth. Visible region, some of them comes to some part. There is some opacity. Atmosphere will kill some part of visible. But if you look at other part of the electromagnetic spectrum, like ultraviolet, X-ray and all, our atmosphere totally blocks it. It doesn't come to Earth at all. Now you may ask, why you want to study the Sun in all those regions? Why can't you study the Sun only in visible and radio, which is coming to us? Why you want to study it in UV and X-ray? That's what something which I've talked maybe 100 times in my talks, and even in MCNS, and maybe 5 times I've talked about this. So those who are here, I'm sorry for that, for making you again boring explanation of this. It's like, blind men looking at an elephant. You put 5 blind men, this is what Sri Ramakrishna Paramahamsa used to sell many times. Any object, if you put 5 blind men to study the sun, study an elephant, they will touch different parts of the elephant, and the person who is touching the tail will say that elephant is like a twine. The person touching the stomach will say that elephant is like a wall. The person touching the legs will say elephant is like a tree, and they may argue each other, elephant is like a tree or a wall. And even if you call an international conference of all the 5 people or 10 people and ask them to present their results and try to make a uniform view of elephant, what you get is a funny elephant, because we put together all their observations. That's what we do in science, right? We get is something like that. That's what is happening in astronomy. Even if you study all this information what we are having, it may not be the real object what we are having. But to reach closer to that object, you still need different observations. If only one person would have taken, we would have reasoned that elephant is a snake and would have closed that chapter, right? So similarly, the sun what you see here, this is sun today, exactly taken an hour before. It is 7 at 2:40 p.m. Taken from a satellite. I just prepared it just before coming here. If you go out now and see through a film, you will see the sun with a nice, beautiful 2 sunspots here, the dark spots. The same sun looked in a different wavelength. You can see here the daytime, if you can visible. This is taken from Solar Dynamic Observatory 1 satellite. This is taken at 1700 Armstrong wavelength at 2022, 25th February 2022, 9:12 UT. So 9:12 UT is 2:42 Indian time, right? So it's 2:42 sun. The same 2 sun looks little different. The same 2 spots you can see here, beautiful dark spots, but the sun looks little different from the previous one. The same thing if I using a ultraviolet spectacle, I allow only ultraviolet rays and block all other rays. This sun looks really different. This is again the same sun at 2:42. It's marked here. The same sun, 2:46 and 16. The same sun, whereas you see the dark spots are gone. If you study the sun in ultraviolet, what you see is a totally different sun. It's like an elephant studying blind men, right? One person will think it is a tree, another person thinks it's a snake. This sun is different from the previous sun. And when you look at it in a different wavelength, it looks really different. And look at those dark regions, it becomes super bright regions. So that dark regions don't emit invisible light, whereas it emits a lot in UV. And a lot of new dark regions have come in UV. So if I put together all these things, and this is the magnetic field measurement which I told in 1908, when Hale measured the magnetic field from the sun, he found that those regions wherever those dark spots are there is a huge magnetic field there. That's how we understood that dark regions are connected to magnetic field. Okay, you just compare these dark 2 regions, there is a lot of magnetic field here. That's how we knew that these dark regions are connected to magnetic field. Now look at the same thing in 4 different wavelengths. It's look really different. So we have to study the sun not just in visible. If you really want to understand the sun, we have to study it in visible, we have to study it in ultraviolet, we have to study it in X-rays, gamma rays, whatever possible ways, polarization, all sorts of spectra, we require that. And atmosphere has other problems. That why I'm answering why we are going to the space. This is something called atmospheric seeing, which you people, those who have swim through a telescope might know. When you look through atmosphere, this problem of atmosphere will kill many of these features. And when you look at the same thing with an adaptive optics or go to the space, you see a different or a better picture, clarity picture. Another advantage is if you go to the space, you can continuously monitor it, right? 24 hours you can monitor it. There is no day and night there. Here the problem is day and night, right? You start in the morning, then a rain came, cloud came, then you waited for the rain to over 10 o'clock. 11 o'clock you start the study. By 3 o'clock, 4 o'clock, sun starts setting. So only 3-4 hours you can study in a day. Whereas if you go to the space, you can 24 hours study. So you have more data and more information. Hence, we decided or people started thinking which is the right place to go. So that was one of the ideas called there are 5 Lagrangian points against any 2-body problem. You take sun, moon, or Earth, moon, or Earth, sun. There are 5 places where gravitational potential goes to 0. The reason is this is potential field lines. if you think of Earth pulling something towards Earth, Sun is also pulling it towards Sun, but still things fall to the Earth because it is close to Earth, right? One by Astra relationship again. But if you keep going away from Sun, Earth, there is a point where the pull by Sun and the pull by Earth cancel each other, right? The gravitational pull by Sun and the gravitational pull by Earth cancel each other. That's a point called L1 point, Lagrangian point. So the gravity becomes zero there. Advantage is if gravity becomes zero there, if you put something there, it will remain there. No need to correct because nobody is pulling it. There's no force there. Whereas if you put a satellite around the Earth, all of a satellite, there is a correction mechanism required. Once in a while, you have to correct it for the orbit. Whereas if you put it here, it is much more stable orbit. You need very little fuel to stay there for a long time. There was one NASA satellite there. NASA placed, of course, first time there. It was a 5-year mission, but without any problem, it remained there for 11 years. Even now, it is there. But our telescopes are all degraded, so people started less using it. So Aditya, India has never gone to this L1 point. So they were decided that if you are going to study the Sun, why don't we go to the L1 point? Because Indian Space Agency was also wanted to technically feel the challenge and accept that challenge and place a satellite at this L1 point. Problem is this L1 point is a virtual point. There is no body there. It's a virtual space, right? Where gravity becomes zero. So for Space Agency also it's a challenge to reach that place and place an orbit, place a satellite in that place, around that place. So that was challenging. That is the L1 comes from. So in my title, wherever Aditya L1 comes, that L1 comes from this Lagrangian 1 point. And another thing is, if you study this eclipse, this is an actual eclipse photo from the Earth. And I'll show you another eclipse. You can see very beautiful things around the Sun, which is called the corona of the Sun, which is seen only during eclipse. I don't know how many of you have seen a full eclipse here, because it happens rarely. In India, it happened in, I think, last corona time, there was one in Himalayas, which was an eclipse. And before that, in 2009 or something, there was a full eclipse in India. But it happens in different parts of the world. There are people chasers which goes to different parts of the Earth and see that. But this corona, speciality of corona is it's very, very, very hot compared to. I'm not going to the details, but corona is almost like 600 times hotter than the Sun, which is itself is a very strange thing. What is the time? Still time? I'm not missing that. Okay, fine. So, because I was thinking whether I should tell why this coronal hot heating problem, because I will take another 2 minutes for that. See, if you have a bulb there, you know that as you go away from the bulb, or if you put a candle here, the hottest place will be close to the candle, right? As you go away from the candle, the distance R increases, the heat reduces, right? So in Sun, energy is produced at the center, and disk is what is emitting it. So the hottest region should be the disk, right? As you go away from the disk, temperature should reduce technically. But in case of Sun, you see the temperature reduces initially, but at some point temperature again starts shooting up. Not just shooting up, it shoots up to, so the temperature of the surface of the Sun is around 6000 Kelvin. It reduces to 4000 Kelvin at some place as you come away from the Sun. But after 4000 Kelvin, what I expect is it will go down again, but it starts shooting up. It shoots up to million Kelvin. It went to million Kelvin so that it produces X-rays. Because, you know, temperature, as temperature increases, the energy of that light also, it starts producing X-rays at Sun surface, it produces visible radiation because it's 4000 Kelvin. But in corona, outside layer, it starts producing X-rays and UV and all. That's why you saw a different Sun altogether earlier. That's called coronal heating problem. We know that magnetic field is playing a role here, but it's not well understood still now. It is considered, if you see Science magazine had when 2000 came, there was a issue with saying that what are the 100 biggest challenges or biggest problems of science, and one of them was this coronal heating problem, because still now it's not very well understood. Now if you look at the eclipse, you have different eclipses at different parts of different seasons or different years. And why this Sun is looking, corona looks like this in one time, after 10 years when they took a photo, the corona looks different. Why is that? That is another question. One way to study is coronagraph. The problem is we cannot study corona because Sun is so bright. The disk of the Sun is so bright, and if you look at the Sun, what you see is you don't see the things around that. So even if there is Sun, if you want to see a car coming, either you put that cover, right? or you have to use your hand to hide the sun, only then you can see around that. So think of things very close to the sun, around the sun. It is very difficult to say. Only option is you have some coin or some occulter, some sort of occulter like a coin, and you block the sun, then you will see things around the sun. Just like how you do while driving. This is the idea of coronagraph, and that is when this idea of Aditya was born. Initially, we thought that we should also have a coronagraph in space where you hide the sun disk so that you can study the things around the sun, like an eclipse. Create an eclipse artificially so that you can always have an eclipse, because you don't have to wait 10 years to have an eclipse. You create an eclipse artificially and study just like whatever we saw the eclipse image all the time. So Aditya-L1, which my topic is, which I'll run through quickly in 20 minutes, is an observatory which has 7 payloads, and it is to be launched this year, and maybe August is what the time we are thinking it will be launched. Everybody is rushing to finish their work and ready to be launched by August, because there is a window for this launch window. After August, it is not possible to launch this year due to some limitations of PSLV and all. Then only in January it is possible, and nobody want to lose 4 months just like that. So everybody is rushing to launch this year. These are 7 payloads. There is one visible emission light coronagraph. There is a solar imaging, ultraviolet imaging telescope, which I personally work on, and there are other X-ray instruments and all. This is how the satellite image looks like. And this will be placed in L1, as I told you. As I told you, there is a very veteran placer person there already, which NASA placed in 1999 when when first human beings went there. Even after that, nobody has gone to L1. So we'll be going and giving a company to SOHO, which is still live and active there. Though we don't use the data much, it is decommissioned officially. There is no funding, but there's no problem. It is very live. People once in a while NASA pings and see that he is happy and healthy like an old man there. So once we go, we will have SOHO will have a company in the same place we are going to place the Aditya. This is the orbit. What we are doing is, this is the L1 point. We will go round. This is actual mission plan, and we are going to place it in a halo orbit around the L1. You may ask, why don't we go more close and keep? There's a problem here. Problem is, the only means of communication which the engineering kids here will immediately relate to that. The problem is, the only way we can communicate with the satellite is through radio waves, radio communication. And sun is a source of lot of radio waves. So if you keep your antenna towards sun, you will see lot of noise. Or Sumana will know that. Sun is the biggest noise for those people who do radio astronomy. They somehow try to get rid of sun, because sun produces a lot of noise. No antenna, if you put the antenna towards sun, you won't be able to communicate with the satellite, because what you capture will be all the noise from the sun. So you don't want to keep your radio antenna, which meant to communicate to the satellite, towards the sun. So we want an angle, little angle, 5-degree angle from the sun, so that sun is in the shadow, we can communicate with the satellite. For that purpose, it is kept in a halo orbit around that place, little away from that center. We don't want in the sun-earth line for the purpose of communication, and we don't have no other way. So it will be kept in a halo orbit around L1 point. It has 7 payloads, as I told you. It's visible emission light coronagraph, and there is an ultraviolet imaging telescope. There are 2 X-ray payloads. One is low energy X-rays and one high energy X-rays. And then there are 3 in situ measurements. What I mean in situ is, these 3 things will measure the environment at L1 point. These 4 are remote sensing. It will be looking at the sun and studying things happening on the sun, whereas the other 3 will study in that local environment. Again, it's a photo of that in the stored condition. The solar panel is in a folded condition. So this is the suit image, and next to is the VLC, the emission and coronagraph. And there are 1 X-ray payload here, you can see inside. And there is 1 X-ray payload here below the suit. Again, there is a small hole here for X-ray to pass in. And there are this magnetometer is folded and kept here. It will be, once it reaches there, it will be deployed like you saw in the previous one. And there are other things as well. Okay, I'll just quickly run through other things. VLC will study the coronagraph. So this is the SOHO which I told you, which was gone to L1 point. The problem with SOHO was, it was 10, 20 years before. The camera was not very good, and they were looking a little far away from the sun. This is the actual eclipse photo taken from Earth using a nice DSLR. Look at the photo taken from Soho, so bad, right? The one which is taken from Earth was much better, right? What we want to achieve is observe these 24 hours. That's what the aim of a chronograph is. But when we sent that 20 years before, what we got is these images. Of course, we did a lot of studies with that. We understood a lot of things about corona after going. So how revolutionized the field of solar physics. But we have not reached anywhere near to this beautiful eclipse time photo. So what we try to do is improve upon SOHO and try to make much close by sun and try to make a much better resolution by better contrast image. That is one of the aim of VLC. And this is a field of view of VLC. Sun will be hidden or occulted, and you will see the things around that, which is a corona. And there is spectroscopy. People who do in science know that how important spectroscopy is. That I'm not going to the details of that. Why is spectroscopy important? Spectroscopy is important. But people who are doing audience in UG and PG knows that how important studying the spectrum is. So we also have a spectroscope with multiple slits. It can scan through that region and through this region and get a lot of information. It can get information like velocity, the plasma density, many things, temperature in that region, etc. So as I told you, the aim is studying the corona, diagnostics of the corona, and physical parameters like temperature, velocity, density, and the fluctuations, and things like, okay, let's keep those details. Again, this is too much scientific. Maybe I can explain. This is basically how we find the temperature of the. You may wonder that when you have a fever, you know how you find the temperature. You put any measuring thing. These days there is infrared measuring things also, which you see. But you need somebody nearby, right? How do we find temperature of the sun, which is so far away? Without a thermometer or going there and measuring, right? So there are ways of measuring temperature. It is only by studying the rays coming from the sun. So here, for example, that one way is to take it in two different wavelengths, like two spectra, which is the green line and the red line, what we say, it's an iron line. And you take a ratio and you see that it is very, very much connected to the temperature, and you get the temperature information through that. That's what VLC is going to do. There are many ways of doing that. Just giving an idea of how spectroscopy can get the temperature. Okay, this is how the temperature varies. You can see during eclipse time, if you take the eclipse data, people have tried taking this green line and red line and taking a ratio and trying to find the temperatures. You see that different eclipse time, you see different types of temperature things. There is a lot of interesting things happening there. So that is why once VLC goes there or Aditya goes there, we will get a lot of answers about this, why this whole variation in eclipse to eclipse, what is happening out there in the corona. This is taken again from Soho Lascaux coronagraph. You see a lot of beautiful things. These are real videos, okay? These are not any artistic impression. With dates, it's written here. You see that there's a comet falling there here. It was an unexpected event happening here. If you see carefully, you see that a comet is going and falling into the sun. Some comets now, when you go nearby, sun simply pulls it into the sun. Apart from that, you see things are being thrown out. A lot of huge chunk of plasma is being thrown out to the space. And you should appreciate it, that you simply think of a stone being thrown away up to the space. So difficult. Think of a shot put you take and throw. Shot put is what? 20 kgs? I don't know. So difficult. The rocket launching. Such a difficult task. Only 6 or 7 countries in the world can do that. So the satellite on the rocket is like 1000 kgs. To send 1000 kg to the space, we need a lot of energy and difficulty. What they are throwing out here is like size of an Earth. Chunk of plasma with mass of an Earth or size of an Earth being thrown to the space. How much energy will be there to do this activity? And Sun's gravity is much, much higher than Earth's gravity. It's more difficult to launch from Sun than from launching from Earth. So the bomb blast happening behind, to throw so much particles to the space, which reach even Earth, the energy required is so high. I just want to show that more. I'll show you one more examples of that, then it will be more clear. And this is the next one what I'm working on, which is Solar Ultraviolet Imaging Telescope. It's a nice telescope which observes the sun in ultraviolet. I already showed you in ultraviolet the sun looks really different from the sun what we see, and we'll be studying it in ultraviolet. I'm not again the details I'm not going to the details because of my time limitation. So I will be, it's a UV telescope and it will study the sun. We will be studying different things on the thing. One of the major things which we will be studying is, which you may easily connect is, you all would have heard about this ozone layer depletion, right? This, you all know that UV, you would have studied in school that we are protected by ozone layer. Ozone layer stops all the UV which is coming from outside to the inside. When you say ozone layer is either depleting or ozone layer is blocking, you also should know what is happening is when ultraviolet rays come, ozone O2 reacts chemically and become O3, right? That's what ozone is created. When you study this ozone layer, you also should know the source of UV. The source of UV is sun. When you say an ozone layer is depleting, going up, you should know that it could be because of the atmospheric chemistry. So if you want to study this atmospheric chemistry, you should know this UV radiation coming from the sun. Sun is the major source of ultraviolet rays, which is reaching Earth. So solar ultraviolet imaging rays, another way is to study this connection between Earth's upper atmosphere, where this ozone layer formation happens, and the source of that ultraviolet, which is the sun. This is what I was talking about earlier, the temperature of the sun. You can see it reduces initially. This is height on the x-axis and temperature on the y-axis. It comes down all the way to 4000 few Kelvin, and it again shoots up at some point. It's called transition region. It shoots up all the way. Temperature is 10,000 here. It shoots up all the way to 1,000,000 Kelvin. Temperature shoots up suddenly. This is what the coronal heating problem, which is known in sun, which is again we are studying in suit. We will not be studying that region, but we will be studying only the up to transition region, below transition. This is the sun, as I told you, looks really different in ultraviolet. This is sun what we see generally if you go to beach or a sunset. But the sun, what we see, going to see, suit is going to image is something like this, which is really different from what we see. But we want to know that. Then only we know the big elephant and the sun. How in totality, what's happening on that. So this shaded region is the one we will be studying. As I told you, the ultraviolet region we will be studying 100 to 400. These are the region which reaches our atmospheric layer, ozone layer, and ozone layer below, above ozone layer, there are regions like ionosphere, for example. So if you want to know how this solar activity affects ionosphere, etc., we want to know, remote sensibly study the variation of the sun and compare how is a lot of people study atmospheric physics studies are happening. So if you want to give data to them, what is coming from the sun, you need to study the sun, and we will be providing that data. Details of the instrument, I'm not going to the details of the instrument, just for I want to give a picture of the instrument, how it looks like. Of course, it will be covered, etc. after this. And a field of view of the sun, I told you the coronagraph will occult the disk, it will hide the disk, whereas our suit will observe the disk. So in combination, if you combine the data of both, at the same time you will study this corona as well as you study the disk. So in combined between these two, you will get the overall picture of the sun and the neighborhood. Okay. These are the details of that, science goals, etc. So we'll be studying different layers of the sun, as I told you. There is also a coupling between the sun. What you see here, I told you the dark spots at the atmosphere looks very bright at the higher up. These are actually images again. The same spot you can see, it becomes brighter. So why is it happening? Why that dark spot is emitting a lot of UV? It's emitting more UV, that's why it's bright. These are the questions which you will be answering, trying to understand. Apart from that, there are the solar flares, which I just told you earlier. There are sudden emission of light or a big bomb blast happening there. I will show you some nice videos instead of showing graphs, which may be of more interest to you. Look at here. This is again real photo. I have put the date, the instrument which is observed, etc. These are real observations. Look at this region. There is a huge chunk of plasma hanging around here. At some point, you will see that it's nicely thrown out. It may look a very smooth thing, but as I told you, to throw out such a big plasma, such a big energy accumulation inside and blast happening. Then only so much plasma can be thrown outside. And say zoomed of the same thing, just to give you a nice see how nice the blast is happening there. These are called solar flares. So we'll be studying these solar flares. Again, it is an ultraviolet, as I told you. It's a multiple wavelength combined, just to give a nice, beautiful view of the sun. And let me tell you, sun is the only star where you can see all this. Take all these photographs. All other stars, you won't see such photographs. And this is another big blast happened. It's called very old one, 1945. The date is here, June 28. It's observed from high altitude observatory on ground. At that time, there was no satellites. You know, Second World War time, there was no satellite. But from ground, people observed this, such a big thing. It's called Big Daddy blast. You see such a big blast happen on the sun. Huge chunk of plasma was thrown out. If people say, if such a thing happened right now, 80% of the satellites will be sometimes burned or pushed down or something, because all this will come and hit us if it is towards us. It will have gravitational pressure on the satellites, it will push down. It will also cause a lot of electromagnetic short circuits on the satellites. It's again just want to show because it's a more popular thing. I thought I'd just show you some nice videos. So what will happen to this thing when this blast happened? It's just that it's not just that sun throws out this. All what sun throws out will, of course, go to the planets, right? Of course, Earth is one of the planets, and it comes and hits the Earth, and it interacts with our atmosphere. It creates burning in our atmosphere. That's something called aurora borealis. You all heard about. Sadly, we Indians cannot see that. But if you have ever gone to high altitude countries, I lived in some high altitude country for almost 2 years. It's not very clearly observable even in Ireland where I was living. But if you go to Norway, Sweden, you keep seeing this atmosphere burning in different colors beautifully. That's because of these things coming from the sun. Apart from that, we have these days you have a lot of aeroplanes passing through the polar regions, going very high. There are satellites up there. All these things which is coming from the sun can directly create problems for them. So I started with saying, though all this study is purely academic, but you see, unlike other astronomy thing, sun is more close to us and it has direct influence on us as well. It's only a big astronomical source. Maybe moon and sun are only, of course, some nearby planets maybe are the only astronomical celestial bodies which has direct influence on us. This is very old news. You can see Solarstrom holds stock market. It is again 20, 50 years before, because it created some power failure at that time. So just wanted to say that though I started saying it won't have influence, it sometimes influence as well. It's more recent news. It came Solarstrom. I'm sure you just simply Google search, Google news about Solarstrom. You'll see a lot of news every day saying that it created that problem, this problem. You don't see in Indian media much because we are safe, because we are in the equatorial region and we are well protected by Earth's magnetic field. But the moment you go to higher latitudes, that creates problems. So there are, the alignment is a very repeated news. You can see that it says that it can create global power failure. It's a little too exaggerated, but still, it can not still. So some questions we are asking, I'm not listing out everything. It's more of an academic thing. Aditya-L1 will be asking this question, which is, how does this solar flares look, emit in different wavelengths? Is there any signature to know when this flare will happen? Can we predict when this flare will happen so that we can inform all the space agencies that, come on, there's a big flare going to happen, shut down your satellites or shut down your whatever protection layers so that these things won't come and interfere with your electronics, your ICs, because these are very high energy particles, right? It can simply pierce through an IC and kill the circuit. It can burn it off. So this radiation damage is a big problem in electronics, space electronics. So people can, if you can forecast it, space agencies can be safe. In fact, I had attended one of the talk by Marshall Space Flight Center, MSFC. They were talking by an astronaut. He was telling that they were planning an EVA, extravehicular activity, going out. You know, the astronaut go out of the module, right, to make a walk, space walk. You have seen a lot of videos. And they were about to enter. So everything was planned. It's automated. At this time, door will open, go inside. But exactly when they were about to open, a solar flare happened, huge flare. And all the X-ray monitors on the module started beeping. Means it started showing that huge X-ray outside. And they immediately had to abort the whole plan. And he was saying that if they would have gone out at that time, maybe they would have got fried because their protection is not enough because of all these energy particles could have simply pierced through them, high energy protons and all those could have created either problem for them, surely cancer for them because they can interact with their cell molecules and create mutations, etc. And so there are a lot of interest in, or interest plus a lot of money there, out there, in the industry as well. to predict whether we can predict these solar flares in advance. Can you say in a day before tomorrow 10 o'clock there will be a flare, so that we all can be safe? So that is the sum of problems. Again, this is a variation of the solar irradiation, etc. I'll quickly run through because I'm very limited by time. This is again X-ray image of the sun. You can see sun is producing X-ray bomb blast once in a regularly. This is a spectra of this. So there are X-ray payloads to study those X-ray things. We have two X-ray payloads, one in soft X-ray and one in hard X-ray. And these are the existing X-ray payloads. Again, this is a little more technical details. The energy range of those X-ray payloads which are existing on the space, and what we are, there's a big gap there. So this is the region we will be filling in Aditya. Solex will be coming there of that range, X-ray energy range, and Helios is another satellite, another instrument on the satellite which will be filling that range. Okay, and there are two in situ instruments also. I have just two more slides. In situ payload means measuring at that place, which is basically those plasma which I showed you coming from the sun. When it reaches this L1 point, analyzing that, there is a plasma analyzer package, and there is also a particle experiment at that place, and also magnetometer. There are three in situ instruments. At L1, when the plasma reaches at L1, it will make the measurements. Okay, these are some questions and answers which instrument will be trying to answer, etc. So in short summary, there are a lot of unanswered questions in solar physics, and Aditya-L1 will be India's first dedicated satellite to study the sun. And the most important thing I want to say is that this is a golden chance for youngsters to enter into the field of solar physics, because first of all, there is a space mission happening. A lot of engineers are working on that. There is especially engineering graduates here, or for people who are interested to move to the science. Also, this is going to produce huge amount of data, right? Who will analyze all this data? Suit alone, I'm saying 21 GB of data every day we are producing. 21 gigabytes of data every day Suit will be producing. Who will look at all this? We need lots of people, maybe 1,000 people working on that. Then only we can extract all the science out of it. And if you take the solar physics community in India, maybe it is 40, 50. So it's such a chance for youngsters, because a lot of data free of cost, no demand, it's available for you. So it's a good chance for youngsters to feel. So I'm slightly advertising as well. I'm seeing some youngsters here sitting here, as well as hopefully some people are watching on YouTube and Teams. So it's, if anybody is interested to do solar physics, this is the right time in India. Okay, these are some images of our instrument being built at ISRO laboratories. Okay, I leave you with one nice movie of a actual observation of a beautiful solar flare which was observed. There is sound of it. Sound maybe I can mute. There is nothing. It's just added sound. It's not sound of sun. Okay, I leave it with this thing. You can meanwhile think about your questions and prepare questions, or maybe I can take over. Let this play. It's called a coronal rain. There was a nice blast here, solar flare. But what happened is all the flare plasma cannot outgo, because sun will pull back now. And some of the plasma was falling back like a rain. Because as it reaches some place, it condenses, and due to gravity, it starts falling back. And because of magnetic field there, magnetic field will channelize plasma, because plasma is energetic particles, you all know, right? And plasma interacts with gyrate, because it's energetic particle. If there's a magnetic field and an energetic particle see a magnetic field, it will gyrate around that, right? So because of that, it was channelized through those magnetic fields, and it showed a very beautiful actual video happening on the sun. It's not any, it's like you go for a hubba, or you see that big patakas which goes up and produces beautiful images right on the sky, and something like that. It's a solar flare happening, and just if you see, just to give an impression, there is an Earth to scale to show how big this is. Earth is of this size, and you can, to the scale, you can see how big this event would have been. And it didn't escape because it was not even having energy, enough energy to escape that surface, and it was falling back. There are so many such observations, but one of them, coronal rain observation. Yeah, I leave you all with this beautiful video, and I'm open to questions.
Thanks, Sreejith. So good, and getting to know about sun a lot. So we'll take some questions from audience as well as from online. First, we'll go for audience.
Yeah, some people here would have heard all this maybe before, because in SRI time I had given a very similar talk in last July or something. Sorry for that, repeating some of those contents.
Your talk is, as usual, excellent. There's 3 thoughts of rise in your talk. And my question is very simple. See, you were in one of your slides, you were talking about temperature variation from the surface of the sun as you go away from the sun.
Yeah.
And you are showing only a few thousand kilometers away from the sun. Am I right?
No, okay, 3,000?
Few tens of thousands,
okay.
Probably.
Yeah.
That's what you are saying.
Okay, let me speak up that thing so that it'll be easier for you to, I can show you directly then. Okay, yeah. Okay, here it is. Yeah.
I mean, kilometers, right?
Yeah, kilometers, yeah.
The last number is 3,000.
Yeah, I have shown up to that, yeah, correct.
Yeah, okay. Within that itself, very significant.
Yeah.
Okay. So,
it's a very sharp actually. This happens in few hundred kilometers. You can see this. If you say this distance, it's around 2,000 to 2,100 or 2,200.
Okay. So, my question is, what is that zero height? Because what I was thinking is, sun, near the surface is more or less somewhat gaseous, and there will be, that surface will be somewhat diffuse. So, there will be some uncertainty in the surface itself. So, when you are showing such a short distance away from the sun, your zero must be clear.
Yeah. Zero is not center of the sun.
Not center of the sun, surface of the sun.
I'll tell you. Surface of the sun is defined by the opacity. So I told you, it's like a black body. There is all the energy inside is absorbed by the molecule. Then it works like a convection. It takes the energy like water boiling. If you boil, make tea in the stove, boil from bottom and look from top, camera top, you'll never see the stove, right? The stove flame you won't be able to see because the vessel is absorbing all the energy from the stove and it is re-emitting to the water and water molecule is taking it forward. Exactly like that happens on the sun. You won't see inside. So that region where that emitting happens, or I can say when you look from top, the vessel surface is there. No, that is where the emitting happens. So we said tau equal to 1 line in physics or the language. That is where the below that is full opaque. So that line can be well defined. So it's not okay. It is a gaseous form, but that emitting line we can define, and that is not one place. That height also varies from case to case. So if there's a magnetic field comes by, it makes a change. Like it goes up and down. But generally, the tau equal to 1 line is considered as the surface of the sun. It's scientifically. But if you really go and measure what is gas, as you rightly told, I just want to show you one thing here. If you see the dotted line here, that is the density. Just want to show you that also. So that's, if you see the solid line, that is temperature. This dotted line is the density of the plasma. So density also, you can see here is the density value. Mass density is written now. So the density, whereas as you rightly told, at this point onwards, it is slowly only falls. So it is like very smoothly falls. And at this point, where the temperature suddenly goes up, you also see a sudden fall in density. When density falls, it goes more gaseous. So as you told, physically it is not a solid. Sun is not a solid. So it is like a gas. So if you really go and like so our probe is going, if you go and probe, you will not be able to see a surface like Earth's surface. But it is defined as per the emitting of light. So by that surface. Yes, sir.
Photons.
Yeah.
Sun is emitting neutrinos.
Yes, very much. So I didn't talk about solar neutrino problem, of course. It's a novel issue. Yeah.
How do we get sun's central temperature? It's not possible. Except with neutrinos.
Yeah.
What you are talking about is surface temperatures, cover a few millions kilometers.
Very correct. Yeah. So what he told is there is, you know about neutrinos, right? I told you earlier that this gamma rays, they're very difficult for them to come out. But neutrinos don't very good. They just simply pass through. They don't have any of this problem. Neutrinos are something which can pass through anything, right? So it won't interact with anything. So a neutrino which happens due to the fusion today will reach Earth today itself. because it can simply pass through. We don't have any problem with any of this crowd. They are the Mayavis. They are special characters.
That is 8 minutes delay.
Correct. Yeah, that delay only. So that delay only, the traveling delay only will happen. There is no other crowd problem there. No scattering problem, I would say. So as he rightly told, though the sun is opaque, the neutrinos from inside can escape. Only for light, electromagnetic radiation, this opaqueness is applicable. So only way to know what is happening inside one of the probe was solar neutrinos. Of course, it got even Nobel Prize because there are some study about solar neutron program. Neutron itself was changing its behavior as it comes from sun to earth. It was just as it's very much like a Mayavi. It changes its color, whatever. So this finding neutrinos is what how to know the inside temperature is we have a theoretical model for a fusion with this plasma using hydrodynamics. What will be the temperature? Based on that, people will see if this is the model is right. This many neutrinos or this type of neutrinos will be emitted. This will be the atmospheric thing. Then you compare it with the observation. Is it matching? And you see that no, it's not matching. You tweak your model again. So the temperature of whatever inside I showed you here, that diagram, that was all model based on theoretical model. Of course, it is validated using either solar neutrino or magnetoseismology, etc. Especially for density magnetic field. But as you told, it is one of the probe.
I have 2 more questions.
Yeah, sure.
Another question is, the planets are not formed from sun. Are the planets formed from sun because the abundances of elements of the planets do not correspond to the abundances of sun?
Now, yeah. So that's I would say again. Yeah. So there is a lot of study happening on that. But as far as my knowledge, the common understanding or the majority in science, I can only say that. I cannot say in science 1:2, and because then there is difference of opinion. But the common knowledge is that other than I think Pluto, all other things might have formed from the sun. There is a reason why I saying that. The beauty of solar system is that all the planets are in same plane. Right? Why should it remain in same plane? If it is coming from outside, it should have been in random orbit. But that's not the case. All of them are in same plane. So the theory which says why it is same plane is because there would have been some disk formation around the star. It could be some sort of accretion disk, not in terms of a star accretion, but some sort of disk was there. And slowly with time, this disk got gravitationally became solid. If that model is true, then we can explain why everything is in one plane. This is one of the things, but abundances also, it is, you see sun has all these abundances. Sun has iron, all these abundances are there. Amount is little less because hydrogen is much higher. That's what you see. I'm not a geology expert, this is my general knowledge. Maybe somebody, a second, I don't know, any idea, some geologist or maybe, I don't know, any of your geology ideas can talk about that. I'm very poor in that. But my understanding is that all these planets have formed from sun. One thing I can say, all these are formed from star because we won't find iron or these are formed from star because we don't find anything other than hydrogen if it is not star. We also know that we have gone through a supernova explosion because we have seen uranium and all those things. They would have formed only through big supernova-like explosion. So we have gone through. All of us have gone through supernova explosion once upon a time because there is iron in our blood. Question. Yeah. You can explain that maybe better.
I have another question.
It's one more right now.
The plasma is.
Yeah, sir, you can.
Sun is throwing out plasma of the size of Earth into the space. And what about the orbits of some asteroids between Mercury and Sun? It will not be.
It gets affected actually. It not only asteroids when
calculated also.
But it has aberrations. It keeps changing actually because of this solar. In our satellites, you talk to ISRO people, they feel this pressure that satellite gets pushed back because of these things. Because something is coming and hitting now. So they see that things get pushed back by this thing. Actually, when the light itself pushes things back slightly, apart from this, particles also comes and push things back. So it gets affected. All of them get perturbed their orbit. Thank you.
Just adding to like this, all stars there is a, if you
nowadays we see through ALMA or some other.
Can you keep it close by because outside they won't hear unless it is through mic.
Yeah. So can you hear me now?
Yeah.
So in all stars, we can see even through ALMA or some other telescopes. So while star formation, so the disks are formed. So it is called the protodisk formation, protostar formation. And these disks are basically, the stars are formed the gas and dust. So, and these disks are made of dust and etc. At some point of time, there are some accumulations of some part of the disk, and these form the basically the planets. So these are the now, widely known or accepted theory of the planet formation. And in fact, there are very good images from ALMA like telescopes where you can see a protostar. Protostar means the stars which is just about to form. So in a higher perspective, if I say in the star formation theory, the sun is like in the stage of hydrogen to helium conversion. This is called the main sequence stage. The protostars are the stars which are about to come to the main sequence stage. And the observations of the distant stars, using this kind of telescope like ALMA or ALMA mainly the submillimeter telescope, you will see the protostars and the planets, new formed planets are surrounding it. I mean, moving around it. So this is the way all the planets are formed. So this is the few things.
Correct. It's called protodisk. Yeah. I didn't get that word.
And I have just few questions. So in this particular spectrum, I can see again a rise in the UV and far UV range.
Yeah.
So is there any again a black body? Is there any possibility at the
second one? No.
Yeah, to temperature black body. So why that is again a peak and
So what happens now? That's not a black body. That is because of the special emissions which was happening in UV.
Okay.
And we know now that is because of magnetic field. Magnetic field is producing additional ultraviolet extreme UV rays like those solar flares you saw, right? It is not the black body. On the black body spectrum, these additional emissions mechanisms are creating those.
And one more thing, you showed in from two lines you estimated from temperature.
Yes.
So is it a line temperature or continuum temperature?
That's continuum.
That's continuum.
Yeah. I didn't go to those details.
Okay. So my question was, I was reading about Lagrange points before, and I read that essentially Lagrange points are unstable equilibrium positions, right?
Yes.
So if you're going to place the Aditya telescope over there, and you said that it is by an offset of 5 degrees from the actual Lagrange point.
Yes.
Is essentially the satellite going to be continually monitored so that it stays in that position? Because one, it's going to get the fact that its solar panels itself can act as solar sails, and considering that it is at a point of unstable equilibrium, any sort of small movement can send it off ejecting, right? So there's going to be energy invested, like literally at every second that's going to.
Okay, so what he was trying to ask is that these lines, if you see here, this is the word, it's called potential field lines. If I put a satellite on a particular line, we expect that body will follow this line in a way. So if you see around Earth, if I place one thing on this place, on this line here, the satellite will go around Earth because that line you can see it is completing around Earth, right? That is what the gravitational potential field line, where the gravitational field is constant. Now, what he's trying to say, what you're saying is at this point, if you look at this L1 point and L5 point, you compare. So in L1 point, it's a very small region. Gravity becomes zero here. You will see that there is no line here between this line and this line. There is a region there, which is a wide region where the gravity there's not much. It's very small amount. But due to some perturbation, something happens, and if the satellite comes and reach this line, for example, it can take two routes. It can either come towards Earth and go around the Earth, or it might even go around the Sun in the other route. Right? That's called the instability here. There are stable points like L5 and L4. You can see that if it is here, L4, and even if you perturb and reach here, still it will go around the L4. It will never escape that region. That's called stable region. That's the question you're asking. Okay, this is unstable. It has its own advantage and disadvantage. 4:55?
It's still time is 10 minutes.
Okay. Okay. So yeah, as you told, first of all, this region is very, though it is unstable equilibrium that way, in this way, but close to alpha, it is not, the effect is very less if you go in between those regions. But there is also correction mechanism, fuel is carried, and there are firing things to, if required, to correct the orbit, and orbits are corrected regularly. But that requirement of orbit correction is much less than if it is just around low Earth orbit.
Right.
But orbit correction has to be there, or it will be lost at some point.
And the Aditya is always pointed towards the sun. The telescopes
Yes.
are always pointed towards the sun.
It's always pointed towards the
It's
sun.
in continuous communication.
Correct. Antennas are on this side and telescopes are looking at the other side.
I had one more question.
Yeah.
Considering that
It's again
L1
up to the chair based on the time.
Yeah, L1.
Yeah, we'll take this.
Yeah, considering that L1 is literally almost in the line of sight between the Earth and the Sun, is there any sort of mechanism on Aditya to prevent noise from the Sun itself?
It is not, that's why we are not clipping at exact line. We are 5 degree every degree. So that our antenna is not seeing the sun. The moment sun comes to your antenna field of view, you'll get noise.
Yeah, that is for comms between the Earth and the satellite itself, right? But what about the readings that are on the satellite?
That's okay. We are looking little like this. 5 degrees, very small. Sun is so big, doesn't make a difference if you look like this or this.
Okay.
Won't make any change.
It becomes.
Yeah.
Okay. Thanks so much. Great talk.
One question, rather,
Yeah.
3 small questions. One is L1 point.
Yeah.
L1 point, what is its distance? Is it scalar? So, I mean, it is just a representation, or does it have a scale?
Yeah, so if you divide it to 10, somehow distance to 10, 1 to 10, suppose, it is one part of that. So 1 is to 9, I would say.
No, we went to Mars last time. We could reach Mars orbit. Is it almost comparable to that distance, or is it much more than that?
Yeah, it's almost comparable.
Yeah. There is a possibility.
Yeah, but only difference is Mars is a body. We know there's a Mars. Here is a virtual region. There is nothing there.
Nothing there to attract it. So we have to.
No, L1 will in a way attract, but you don't see anything. You cannot visibly.
No, I just counting the distance only.
Yeah, distance will be similar.
Satellite up to that level.
Technology is very similar only as we go to Mars. But Mars, we have a very good. We know where the Mars is going, etc. This region is a little tricky, but similar.
And second question is, you said that due to solar flares and all, even the satellites get pushed.
Yes. Yes.
What is its risk there? Is it going to be affected terribly in that region?
No, so there also this pressure it will feel. It will get that push.
Should be manageable.
So that's why they have to correct it once in a while.
That's okay.
Yeah.
But is it not going to be a very?
No, it will not go totally out of it. But yeah.
And thirdly, he also said that the planets are formed due to some materials which have escaped from the sun and things like that. Are these asteroids eventually will they lead to formation of planets in future? Because they are also chunks of material.
No idea. I don't know whether asteroids merge together and form planets. I don't know. Planets broke and formed.
There was a planet between Mars and somehow brooks and break it out and
formed the asteroids. I don't know.
And then whenever we have studied the asteroids, some material, do they all conform to the same kind of composition?
Means all the asteroids in the asteroid belt are the same material.
When you said it's a breaking up of the planet, are they comparable, those things?
Elemental abundance.
I think more or less comparable. There was one NASA satellite which
went into Japanese.
I forgot the name of the satellite.
Japanese, no?
That is just Hayabusa.
Hayabusa, yeah.
One of the asteroids.
Problem is that since the asteroids don't emit now, finding the elemental abundance is very difficult. Either you go and take it, or some fluorescence or something you have to do.
Okay, so we have second talk. So thanks, Sreejith, for this wonderful talk. And if you need any more discussion, please contact Sreejith. He's here. So thanks very much.
Thank you.
Yeah.
We can pick
Yeah,
the
we'll
key.
start 5.
സൂപ്പറായി ഞാൻ ത്രൂ ഔട്ട് ഞാൻ
Ready?